Welcome to Study Loop.
This question gives us data for 8 planets of the solar system. Precisely, it tells us what is the semi-major axis and the orbital period for each of those planets. Then, it asks us a bunch of questions about that data. Let's begin by remembering about what is the semi-major axis and what is the orbital period. So suppose that a big star, maybe our Sun, is this one. Now, there is some planets orbiting around that big star. Let me draw the orbit of one of those planets. We know that the orbit is like an ellipse, so something like that. Then, our planet goes around the Sun on top of that ellipse, like this. The semi-major axis is this distance in between the center of the ellipse and the outermost part of that ellipse. This is the semi-major axis. The orbital period, on the other hand, is the time that planet takes to complete a revolution around the Sun on top of that ellipse. Now we can begin the question. So let me erase that drawing so that we can begin the first item. We begin the first item by making a plot of t squared versus a to the third, and that plot is as follows. In order to reproduce that plot, you have to convert the orbital period from days to seconds and the semi-major axis from 10 to the 6 kilometers into meters. To convert from days into seconds is not that difficult. All you have to do is multiply the number of days by 24 because we have 24 hours in each day. Then you multiply the result by 60 because we have 60 minutes in each hour. And finally, you multiply this result by 60 again because we have 60 seconds in each minute. This will give you the number of seconds in each day. And to convert from 10 to the 6 kilometers into meters is kind of straightforward. You just keep that 10 to the 6th and you multiply that by 10 to the 3rd because each kilo is a 10 to the 3rd. Then, one of this unit, 10 to the 6th kilometer, is the same as 10 to the 9 meters. By doing that and making a plot of t squared by a to the 3rd, you will get a plot that is just like this one. And this plot has an interesting feature, which is the following. If you connect all of those points, you will get a straight line. Now we have to explain why is this the case. For that, all you have to do is remember about Kepler's third law. Kepler's third law tells us that the square of the orbital period, so t squared, is proportional to the semi-major axis a cubed. So this is what Kepler's third law tells us. In other words, we can say that t squared is equals to some unknown coefficient, let me call it gamma, times a to the 3rd. Then you can see that plotting t squared versus a to the 3rd will be a straight line. Now, just in case you're interested, and we will need that coefficient gamma is actually well known. So, using the known value for the gamma coefficient, we have t squared being equals to 4 pi squared divided by the Newton constant times the mass of the Sun times a to the 3rd. This is the complete form of Kepler's third law. Now you might notice something in this plot. We plotted 8 points, but we can only see 1, 2, 3, 4 points. Where are the other 4 points? The answer is the following. They are right here, one on top of the other. If you zoom in that plot, you will be able to see them. This happened because our data have a very big amplitude. In this case, it's better to do a log plot instead of a linear plot like this one. This is what the question asks us to do next, and by doing that we get the following. Now we have a plot of the logarithm of the orbital period versus the logarithm of the semi-major axis. Now, as you can see, this plot is again a straight line. If you connect all of those points, we still get a straight line. Why is this the case? To see that, we can begin from this equation for Kepler's third law. Taking the logarithm of this equation, we get the following. So the logarithm of t squared is equals to the logarithm of that complicated coefficient, let me call this gamma, times a to the 3rd. Then you use the property that the logarithm of t squared is equals to 2 times the logarithm of t. Also, the logarithm of gamma times a to the third is equals to the logarithm of gamma plus the logarithm of a to the third. Now, you can say that 2 times the logarithm of t is equals to the logarithm of gamma plus 3 times the logarithm of a. And finally, by dividing everything by 2, you get that the logarithm of t is equals to 1 over 2 times the logarithm of that complicated coefficient plus 3 over 2 times the logarithm of a. So, as you can see, the logarithm of t as a function of the logarithm of a is a first degree function. That is, this is of the form y is equals to some constant coefficient b plus some coefficient a times x. Then we expect this plot to be a straight line, and this is why the plot is still a straight line. Now we proceed to the second item. In the second item, we still use this plot and we still use all of these equations. We have to tell what would be the coefficient of that straight line according to Kepler's third law. According to Kepler's third law, we know that t squared is equal to this complicated coefficient times a to the third. Then, by doing what we have just done, taking the logarithm of both sides, we get the following. The logarithm of t is equal to 1/2 times the logarithm of that complicated coefficient plus 3 over 2 times the logarithm of a. Then, as you can see, when we look at this equation like a first degree equation, we see that the linear coefficient of that straight line should be 3 over 2. So this is the expected value. Now we have to tell if our plot has the correct slope. For that, we use the computer to perform a linear fit of this data on a straight line. By doing that, we get a slope that is 1.4986, which is approximately 1.5, which would be equivalent to 3 over 2, meaning that our data has a very good agreement with the theory. In the third item, we are given the value of Newton's constant, and we are asked to calculate what is the mass of the Sun, ms, using our fit. So according to our fit, the slope is this one that I had just said, and the linear coefficient, that is 1/2 times the logarithm of that complicated gamma, is approximately minus 9.2476. That is, b is equals to minus 9.2476. Now, how can we use this data to evaluate the mass of the Sun? We begin by equating 1 over 2 logarithm of gamma with this. By doing that, we get the following. 1 over 2 times the logarithm of gamma is equals to minus 9.2476. Now, we can send 1 over 2 inside the logarithm as a square root. So the logarithm of the square root of gamma, or gamma to the power of 1/2, is equals to minus 9.2476. Now exponentiate both sides of this equation. So 10 to the logarithm of the square root of gamma is equals to 10 to minus 9.2476. Now, since we were using logarithm in base 10, we can simplify 10 with the logarithm, like that. And we are left with the following equation. The square root of gamma is equals to 10 to minus 9.2476. Now we have to use that equation for the complicated coefficient gamma, which is this one. Then what we know is that the square root of 4 pi squared divided by g times the mass of the Sun is equals to 10 to minus 9.2476. Now we square both sides to get the following. 4 pi squared divided by g, mass of the Sun, is equals to 10 to minus 9.2476, and this is squared. Now we solve for the mass of the Sun. To do that, we send this number to the left-hand side dividing and the mass of the Sun to the right-hand side multiplying. By doing that, we get the following. The mass of the Sun is equals to g dividing the Newton constant times 10 to minus 9.2476 squared and this whole thing is dividing 4 times pi squared. Then by plugging in the value of Newton's constant, we get the following. The mass of the Sun is equals to 6.674 times 10 to minus 11 times 10 to minus 9.2476 squared, dividing 4 times pi squared. And by solving that calculation, we get a value that is approximately 1.85 times 10 to the third kilograms. By looking at the appendix, so let me call this the mass of the Sun according to the Appendix F, we have a value of 1.99 times 10 to the third kilograms. So as you can see, we have a value that has the same order of magnitude as the value in the appendix, meaning that our data is good and our calculations were good too. Now for the margin of error, we can do the following. The error, let me call this epsilon, is equals to 1 minus 1.85 times 10 to the 30 divided by 1.99 times 10 to the 30. This results in an error of approximately 0.07 or 7%. So our result has a good agreement with the reference value. Now, before beginning the last item, let me organize my board to keep only things that we are going to use. Okay, in the last item, we are given the value of the orbital period for the asteroid Vesta, and we have to evaluate what is the semi-major axis of its orbit. For that, we can use Kepler's third law, which is this one. All we have to do is the following. We have to solve this equation for A, plug in the values that were given, and then get the result. So we begin by solving this equation for A. For that, we send this term to the other side dividing. By doing that, we get the following. A to the third is equals to t squared divided by 4 pi squared divided by g times the mass of the Sun. Now we take the cube root, and by doing that we get that A is equals to the cube root of t squared divided by 4 pi squared divided by g times the mass of the Sun. Then by simplifying this equation we get the following. A is equals to the cube root of t squared times the Newton constant g times the mass of the Sun, and all this is divided by 4 times pi squared. Now all we have to do is plug in the values that were given by the problem. So we have the cube root of t squared. T is the orbital period, but the orbital period was given in days. Before plugging into this equation, we have to convert it into seconds. This is not difficult to do. Let's do it here. We have that period in days. Now we have to convert it to seconds. What can we do? We just have to multiply it by 24 because each day has 24 hours, then by 60 because each hour has 60 minutes, and then by 60 again because each minute has 60 seconds. And voila, it's already converted. Now we square it, and then multiply by the Newton constant, which is 6.674 times 10 to minus 11, and finally we multiply by the mass of the Sun. For this item, I'm using the mass of the Sun that is given in the appendix. So 1.99 times 10 to the third. And to finish, we divide this whole equation by 4 times pi squared. Then, by solving this calculation, we get a value for the semi-major axis of the orbit of the asteroid Vesta that is approximately 3.53 times 10 to the 11 meters. Now, to compare this value with the values that were given by the problem in the table, we have to convert it into kilometers. And to do that, we divide by 10 to the third to get the following. This is the same as 3.53 times 10 to the 8 kilometers. But now we have to write it like 10 to the 6 kilometers. Then we can split this value as follows. This is 3.53 times 10 to the second times 10 to the 6th kilometers. Now we can compare 3.53 with the values that were given by the problem in that table. To make that comparison, it's easier to write 3.53 as 353. Then, comparing with the values, we conclude that the Vesta asteroid orbits in between Mars and Jupiter. With that, we finish this long question. The numerical answers are circled in green.